Hello, everyone. I'm Indy Ray. I'm lead programmer at Telltale Games, and this is my talk on non-photorealistic light rendering at Telltale Games. So a quick overview of what we're going to do. First, a bit about me and a bit about Telltale and our old tools and the like. We'll talk briefly about our path to Unreal, and then kind of the two major elements of our talk. I'm going to introduce kind of the basic architecture of TTRender, our plugin renderer for Unreal, and then go into some details about some of our non-photorealistic rendering techniques, and then we should hopefully have some time for questions, and then we'll be done. So about me, Indy Ray, as I said, lead programmer at Telltale Games. I've been in the industry for about 20 years. I originally got started in some Unreal Engine 2 and 3 games. Since I've really specialized as a graphics engineer, working both in proprietary engines as well as multiple Unreal Engine games. I came to Telltale Games as a graphics engineer, originally around 2016, worked on a few games there, and snuck out before the train wreck of Unity, and it's the collapse of the company. I've since joined the company again back in 2020 as lead programmer on the team, specifically as we are working on Wolf Among Us 2. Excuse me. So Telltale Games, if you're not familiar, the company was originally founded around 2004 with Telltale Texas Hold'em. We've since worked on many narrative and storytelling focused games. The Walking Dead was kind of one of our initial breakout hits. Wolf Among Us was quite beloved. The studio shut down in 2018, and recently in about 2020, we've been trying to reboot the studio, and with our partners shipped The Expanse and are trying to get Wolf Among Us 2 out. Our games have, from a graphical and style perspective, have generally focused on non-photorealistic rendering techniques, a lot of kind of comic book styles, with experimenting with a lot of the different dramatic lighting, and we often use lighting and style to help tell our stories. So historically at Telltale, we had been a studio that had worked with our own internal proprietary engine. It's known as the Telltale Tool, or T3 internally. It was a really purpose-built engine built around its editor, specifically focused on its cinematic and animation workflows, since most of our games are shot-based, really taking inspiration from kind of movies and television in that sense. The engine and renderer were really built to deploy to platforms from very low-end OpenGL ES2 on Android all the way to high-end consoles and PC. At the height, we would ship on 10-plus platforms. And we built a lot of good content with that engine. So with the reboot, we're a smaller team now, and we need to kind of figure out what the future of our team is. So we've decided to switch to Unreal Engine 4. There are good advantages that come with that switch. So there's a lot of good systems in Unreal for gameplay and prototyping. In our old tool set, some of our gameplay innovation was really being stifled by our old tools. And now as a small team, we have to recruit we have a larger talent pool to recruit from, which is nice since as a smaller team, we have less of a ability to onboard people than we used to. However, it's not without its challenges. So Sequencer really wasn't up to our expectations, coming from a tool that was so finely tuned on narrative and cinematic content. And we really were trying to figure out, how we were going to make games that really felt our signature Telltale style. in Unreal Engine, and that's what this talk is going to be about. We kind of knew that doing such would require some pretty large changes to Unreal's rendering pipeline, and so we had to think about how we were kind of going to do that. And with large changes in Unreal, they come with a lot of maintenance costs. I've worked on quite a few games in Unreal that spent, would spend upward of 3 months on a merge, especially in the renderer. Frankly, Epic doesn't really care about your changes. The merges were really costly, and sometimes I find teams try to kind of solve this by being like, okay, we're going to take like Unreal 2.8, and that's going to be our last version, and then we're going to ship. But we were really trying to build a pipeline that would persist and allow us to build storytelling games going in the future, so we weren't really planning to say last version. And with Unreal Engine 5 looming on the horizon, we knew that some of our changes, the scale of our changes and the merges were going to be exacerbated. So kind of going back a little bit into Wolf Among Us 1 and its style, and thinking about how we would do it for Wolf Among Us 2. So Wolf Among Us 1 is very comic book inspired, film noir. Lots of bright neon colors, strong transitions in lighting, a lot of line work and cell shading. Honestly, it was one of our most stylistic Telltale games. In order to do that, generally the characters and some objects were lit separately in isolation from their environment. We'd have these light rigs that would allow artists to light them separately. And then generally the environments were baked in Maya with a lot of laborious hand-painted touch-ups. Honestly, it was a very expensive game to light. For Wolf Among Us 2, we really wanted to stay true to the original while taking advantage of some new technologies. Thinking specifically about Wolf Among Us, we knew some features, one in particular, light party groups, which I'll get into, we knew were going to be very difficult in Unreal Engine. Specifically, this feature requires global access to light lists in the fragment shader, and that's difficult in Unreal. Unreal's standard renderer, at least it was in Unreal 4 when we started this, was a multipass deferred renderer, which didn't give us global access to light lists. They did have some alternatives there for and tiled renderers, but both had deficiencies and were going to require a large amount of work on our end to get to do what we needed to with them. And based on my own personal experience, I wasn't really keen on taking all that burden of maintenance. So we kind of had to think about this a little bit and how we were going to solve this and do the techniques we needed to do for the Wolf Among Us. So when thinking through this problem, we realized, really lighting was the sort of thing we needed to solve. And, we fundamentally knew how to solve it from a rendering perspective. We'd done it on our previous games in our proprietary renderer. And so Unreal was just really causing a problem. So we were trying to figure out, is there a way we could solve the problems like we're used to and not really be stifled by Unreal Engine? So kind of the big idea here that we noticed and the key thing we realized was that gbuffers actually provided this nice kind of stable API with Unreal Engine. They, generally maintain through the different versions. They, have a nice, pretty standard format since they have to interact with hardware, and they have some nice stable. So we thought, like, could we build a plug-in renderer that really only concerns itself with the things that Unreal doesn't do well, so lighting, some NPR effects, and could we just plug that in? So that's what we started to build. We started to build a plugin, a DX12-based plugin renderer. that was initially built in isolation, so it builds separately from Unreal, and then plug it into Unreal so it can take care of lighting and NPR effects. I'll go over that briefly a little bit. This is kind of vaguely how it looks like. We kind of still have Unreal. Unreal still does its scene management. It handles materials and geometry, most of our resources, general scene data like lights. Once those are shaded, we have an Unreal plugin. It's our TTRender plugin that kind of takes over. It's in charge of hooking the frame and doing kind of basic data type conversion between Unreal and our plugins data types. It also handles mapping of buffers between Unreal Engine and its gbuffer and shadow buffer formats into the inputs of TTRender. And then TTRender itself, which is a DLL plugin that we can load and reload. It does most of the lighting, things concerned with lighting, so it'll bind all of those buffers, bind the resources it cares about. It handles light tiling, all of our lighting computations. It does some non-photolistic rendering effects, and then at the end, kind of Unreal takes back over and does some of its post-process effects, such as color correction and anti-aliasing. I won't go into too many details about the actual architecture of TTRender itself. It's pretty bog standard, since it doesn't really have to care much about geometry or a lot of the things. It's just a pretty bog standard. It mostly just handles lighting. It's mostly compute shader based, and it does mostly bindless. And honestly, it's pretty boring. Some fun things we did do getting started on this is we really wanted to prototype this, and we wanted to make a lot of progress prototyping the system without really having to get into the depths of Unreal Engine. So really the first step we did is we took this great tool that we all know and love, RenderDoc. We set up a couple test scenes in Unreal Engine. We grabbed some captures. And with some fairly simple Python scripts, it was really easy to dump those buffers and build scripts that would dump those buffers to EXRs, which we would combine into EXR stacks. And then we could use our TTRender host to load those up and bind them. And we use that for the initial prototyping and iteration. We had initially hard-coded lighting parameters, which we sense, we can sense load from disk to match Unreal's formats. We don't use RenderDoc and those scripts very much anymore, but we have added a button to Unreal that allows us to dump the buffers, which is really useful for building test cases or just doing general iteration on the renderer itself, since our renderer can build in about a second, as opposed to basically anything in Unreal, which is not nearly as quick. Now trying to bind our render itself into Unreal was surprisingly easy, honestly. I was surprised how quickly we got this working. So one of the key bits here is you have the onresolved scene color render target callback, which is a callback that you can hook on the Unreal render thread. That gives you a hook after the gbuffer is done. Also, the scene color target is done. For our initial implementations, we would just clear the Unreal scene color and render on top of it. We honestly let Unreal keep rendering for, I'm kind of ashamed to say how long, but luckily once we turned it off, the game just got a lot quicker, and I was this great hero because, saved 10 milliseconds. But later, eventually, we got around to disabling all of Unreal's lighting passes, and that was great. The other key bits is you can kind of just dig in and pretty easily get your D3D12 native resources from all of Unreal's things. You can get the command queue that you can use to build your own command buffers. And you can grab the native resources for the gbuffers and shadow buffers. It's pretty similar on most of the platforms. Similarly, we go through, and it's quite trivial to get most of the scene info you care about. So, I mean, the primary scene info we care about is lighting parameters. So you can go through their scene renderer, and they have a bunch of light info and similar info for other types to get lighting parameters that we just marshal into our own data types. It was a pretty simple system to set up. And then for kind of expanded properties that we needed to expose, we also continued to use the scene proxy system, as it's a pretty decent system to get additional data into the render thread, and wasn't too much of a burden. Where we can, we use the existing light components in Unreal and their properties. So things like light positions and intensities, basic colors, shadow parameters, we normally get straight from Unreal's properties. This is really nice because there was a lot of art development going on in native Unreal Engine initially. So it was nice to be able to just turn on Unreal and have kind of a plausible scene set up. But for extended data, we ended up creating additional TT Light components, which are just added to the same actors. And that's nice because that allows all that to live in our plugins instead of having to, increase merges in Unreal. It's not necessarily ideal from a user experience perspective, since they have to find the other component and add them, and there's also some things I haven't given proper UIs to. But honestly, once the artists have gotten kind of used to it, they don't really complain. So doing all this, we still have had to go into the engine and make some changes in Unreal itself. We try to keep that as minimal as possible, to the point that most engineers on the team rarely build Unreal Engine, that they normally work with Unreal Engine from CI. But we have had to make some changes into Unreal. The big one is we've had to add an additional gbuffer and a buffer to that layout, which really gets into, most of that just is properties that get input from materials. It is a fairly invasive change. It kind of goes all over the place. It's pretty straightforward, but it kind of goes everywhere. Honestly, if there was a system that I feel like Epic should really invest in abstracting a bit, it would be that one, as pretty much most Unreal Engine games I've worked on have had to make changes to the gbuffer layout, and it's one of the big factors in merges. The other big change that we generally do is we've added, this are we rendering for TTRender? Don't do all of these things, which is actually a pretty easy patch set to apply to newer versions. Briefly, I'll just talk a little bit about our materials. So all of our materials are managed in Unreal Engine using Material Graph. We're a small team, so they are basically mostly managed by engineering with a collaboration from TechArt. We kind of take a Uber shader approach, so it's a very small set of base materials, and we kind of heavily use material functions. So building a DX12 renderer, you kind of have the question of consoles. So honestly, consoles are a bit work in progress. We obviously have to invest in porting our renderer to consoles, and that comes with a cost. Having done a lot of porting work at Telltale and previous places, and given the small scale of our renderer, it doesn't really care too much about binding resources or geometry. It's a pretty low burden port, so based on the other savings that we got, we thought it would be worth it. With hindsight, if someone were asking me if they would do this again, I think it was a good idea, but I would also propose some alternative ideas. I think you could build a very similar system just using Unreal's RHI. The advantage of that is you wouldn't have the platform problems. You wouldn't have to do a custom port to platforms. On the other side, you have to kind of now run in Unreal's Unreal's context, which you know I feel would hurt some iteration. And then Unreal's RHI, it's more stable than a lot of Unreal systems, but they do still like to refactor it without concern for anyone else. And I think another potential idea that we've kind of since discovered is you could potentially use like the forward plus pass, but instead of trying to like fully forward pass, or even the tile deferred pass, but instead of it trying to like fully get that up to snuff in kind of Unreal's standard capacity, you could still use the platform APIs like DX12 to bind a bunch of custom descriptors and then just kind of do shader injection to really take over and do your own lighting directly there. I think that would be a potentially good approach. It would be probably a little bit more burdensome in the merge, but it would be a bit more integrated, could work better with transparencies and that sort of thing. Kind of want to talk a little bit about how we've seen this, how this went a little bit. So the initial implementation took us about 2 months. In total, we've spent about 1.5 years of engineering time on it. That's between the kind of the technical implementation of the system, the architecture, along with kind of effect work and style work. And then on comparison, I think when we look at the time we spend doing merges, it's actually, I would say, a huge win. So the initial Unreal Engine 4 to Unreal Engine 5 merge took us about a month for like entirely feature complete work. We had actually about a week and a half in, most of our systems and the artists already kind of up and working, but about a month in, all of our features were working again. Successive merges have generally, so 5.1 to 5.2, well, that sort of thing, has generally been between 1 and 5 days. And with these times and investments, we get almost complete control of our look. And it's really just been a huge win in iteration. Like on top of being able to do really easy shader replacements, we can reload our entire renderer. We can, we have test passes that can re-render a bunch of scenes out of their frames. And we really see it as an investment in our future games and titles. So now I'm going to kind of jump into what I see as the second half of my talk, where I want to talk about some of the actual specific effects that we use for The Wolf Among Us. So returning a bit back to The Wolf Among Us 1, right? So at Telltale, we normally have very like comic book inspired looks. Our scenes are generally shot-based scenes, right, kind of from that movie and television heritage. And we do have some free walk scenes, so we do need to have a solution for those, and kind of our investment in gameplay going forward, we want to have more, but they aren't the primary set of scenes on our games. Wolf Among Us itself is very like film noir, very cartoony outlines, shading, that sort of thing. We have very strong transitions between different colors of light and shadow. We rely a lot on our graphic black shadows. And in order to do that, Wolf Among Us 1 was lit with a lot of isolation between different items and specifically characters. They were all lit with their own separate light rigs. We had this system of light priority that I will go into some detail in a little bit. All the backgrounds were painted, as I said, and we rely pretty heavily on invert lines, which you can't see very well in this screenshot, at least on the projector. So for Wolf Among Us 2, we kind of wanted to do the Wolf Among Us next gen. So we wanted to keep kind of the strong style, the good artistic control of the original. We wanted to really improve on that really painful environment lighting process. It would take often 8 hours to do baking of some of our bigger scenes, and then oftentimes artists had to go in and repaint things. That was pretty shitty, honestly. And we wanted to just improve iteration in general and the flexibility of our system. And so in order to do that, we decided we were going to lean heavily into dynamic lights. We weren't going to support any sort of light baking, which really wasn't a huge burden for us because given just the style of specifically the Wolf, it doesn't really rely on GI. So that wasn't really a current concern for this game. We are going to rebuild light priority system, lean heavily in light object grouping, and kind of think a lot about this idea of painting with lights, right? Like before, the artist would paint the backgrounds in Photoshop. We wanted to have them be able to paint the environments with dynamic lights. We don't really have this grand unified theory of NPR like you do with PBR, but we are just building tools for our artists to get their job done. So for kind of the Wolf Among Us, the kind of big effects that I'm going to briefly go over here are invert lines. So these are your standard outlines, but they show up in the shadows. We have some lighting features. Light priority groups is basically this feature where if you have two lights affecting an object, one light, instead of having them blend nicely as you would in a PBR system, we actually want this harsh cutoff between them. So we want to be to decide and have the artist control how to decide which one should take priority for any particular pixel. Light group masks, which is Unreal already has kind of a system to say this light only affects this object, but it's pretty limited. So we wanted to be to lean hard into that and have lots of groups. We wanted to be able to apply shadows more deliberately through the scene, and then we have a gradient system that gets a surprising amount of work. This is a scene from Wolf Among Us 2. It's an apartment scene. We'll return to this and some other production scenes as we kind of go through some of the effects. So to start, invert lines. So in Wolf Among Us, we have a lot of dark shadows. And if we just kind of let dark shadows go everywhere, it would be kind of a boring game and players wouldn't really be able to tell what's going on. So we rely pretty heavily on invert lines, which is where we use the same kind of outlines that you do normally, but when they fall into a shadow, we can give them some light. And so this works generally with our it's integrated into our lighting system, so any light in our game can be assigned to light specifically only lit objects or lines in invert lines in the shadow or both. And it generally works with all of our lighting features. In this case, this scene, you're looking at basically a spotlight, which is the white spotlight, along with a omni light, which is lighting the invert lines. This omni light has a gradient from red to blue applied to it. You can see in our previous scene, this is the apartment scene with all of its invert lines. And then the scene without the invert lines applied. And then once we apply those, you get how it looks in the game. Yep. So there's that. Yep. I'll try to do that some more. So light priority groups is kind of our Next, main system. So generally when you have two lights, say in this case, right, an orange and a teal light, and they overlap, right, those colors mix, and that's accurate and good and all, but we're kind of really going for this comic book light, and we really want the orange and the teal to shine, and we don't really want these like medium yellows in our game. They kind of dilute the style a bit. So how the light priority system works is you can attach any series of lights to a light priority group, and for all of the lights in a light priority group, only the one with the highest priority for any particular pixel actually takes precedence. So there are some controls for that. So the actual computed intensity is part of the priority, but then also artists have additional controls so that they can adjust any particular light to take precedence for any reason they may want artistically. An example shot from our trailer here is Big B Wolf. In this case, light priority group isn't applied. You can see how kind of on his shirt there's some kind of bluing washed in there. And so when we apply light priority groups, that kind of gets a lot stronger. You can see the blue from his blue key light still hits his shoulder and some other little elements where the yellow light isn't really taking effect, which gives us a nice look there. And then just so you can see, if we turn off the yellow light entirely, that's what the key light would look like on him. This ends up being really important under motion, as that yellow light, for instance, in this scene pans over him, he kind of can stand out like this in the shadow, and then as it pans over, it still looks nice and strong. I'll toggle these a bit again. So our light group mask system, it's pretty simple, but we've dedicated a bunch of it because the artists like to be able to control where their lights are falling, especially if we're trying to let them paint with lights. So basically, any light and/or object can have any set series of groups applied on them, and it works basically like a bit mask. If there's any match between the light and the object, the light applies. So in this scene, we have we have a TV, obviously, and we have two walls. So one wall has a light group applied to it that allows only the green outlines on it. The other has red outlines. And then so if the artist wants to apply some lights to it, so you can have an orange light, and you can say assign that specifically only to one wall. You can do that with another light, apply that to the other wall, and then say if you want an additional light that applies to both walls, you can do that, and that works properly. And then this obviously works well with our light priority system as well. To kind of see a little bit how that can work in some scenes, so I'll just kind of do a quick run through of the apartment scene and some of the light priority groups, or the light group masks that are assigned in it. So often a lot of the walls in one room may be on one light group mask. The floors are often separated, as artists will like to be to paint kind of certain shapes on the floors. Some props may be isolated. In this case, I think the candles have been pulled out just so they can be specifically affected by specular lights to get those specular hits on them. And then artists will often separate rooms, so we don't get any weird fall off between rooms. And then the characters are almost all isolated. And to something I won't really go into much detail of, but in addition to this, we also spend 8 bits on a lighting object ID, and that's primarily used for characters so that we can have more than we can use our 24 groups mostly for environments. We have 8 IDs, which gives us about 256 specific entities that a light can apply to. This is mostly used for character-specific lighting. Each of our character gets a specific light rig that only affects them. And you can see, I'll flip through these. That's how the scene's brought together. Really briefly, now that we have all of these lights all over the place, our shadows would get really muddy or overlapped if everything was just casting their own shadow. So really, to deal with shadows, artists all place shadows individually. We just allow for specific lights that are set up as shadow casters. And then those shadows are just applied onto any light within their group, which gives artists a lot of control over how shadows fall. I am now going to finish with a brief overview of kind of our gradient system. So this was originally a system that we had built. We'd built a gradient system for our volumetrics. But then as the artists kept wanting to do more and more, we kind of just realized we could replace the color value in our lights with a general gradient stack. So we have a stack of gradients, and they're just applied they just multiplied on top of each other. And they can all be parameterized on some different values. So in this case, right, we have a simple light. I think it's an omni light, but it might be a point light with a gradient from, I think it's this way. I think it's blue to red to green. And that's just applied linearly through space. So the artist can change the scale at which it applies through the worlds. Additionally, you can parameterize it over distance from the light. So in this case, the gradient is applied based on the distance from the point of the light itself. That can also be scaled, obviously. Gradients can, be interpolated linearly or stepped. Gradients can alternatively, instead of being parameterized, say from distance from the point, it can be based on the surface normal. So against an artist-controlled surface normal, the artist can point to surface normal in any direction, and based on the dot product between that artist-provided normal and the surface normal, we can apply the gradient. And additionally, we allow kind of a newer feature we've implemented, which is getting some use, is we can do light intensity gradients. And in this case, what we do is we compute the intensity of the light. So we actually do the lighting computation through our standard BRDF. And the value out of that we use as the input to the gradient function. And so we then apply just that color against the light. To then extend this, we've also allowed, we have a similar thing we call light intensity override, where we do the same intensity, lighting intensity computation. We feed that into the gradient, and then we just apply that gradient itself directly as the value of the light and throw the intensity away. Obviously, I think an artist will generally do that and ramp it down to 0, so it looks more reasonable. And they will often use that with stepped lighting or kind of just even shorter bands of gradient lighting to get kind of cell shading style effects that are much more manually controlled than our standard cell shading system. And this all works with all of our light features, including shadows. In our games, just from our style, gradients are really important. You can see a few shots here. These are from the trailers where we just have nice little splashes of color with gradients. However, we do find they actually are sometimes used in ways you wouldn't necessarily anticipate. Here is a shot. One of our screenshots with all of the gradients removed. He is fully lit, but as you can see, it's pretty flat. And the artist will then kind of on top of that, since we do have a shot-based workflow, apply gradients in a fashion that allows them to kind of really get some nice gradation across their face and really just direct the light as they like. So that's most of our techniques. I think some kind of takeaways here is I think you can really just use a part of Unreal that work for you and take ownership of the parts of Unreal, of the things that make your game unique. Doing non-realistic rendering by just equipping your artists with really powerful tools. And also just really focusing on iteration, whether that's iteration time for you as an engineer or iteration time for your artists. I wanted to give some special thanks, obviously, to the entire Telltale team, but specifically Brett Rogstad, our primary lighting artist, who really honestly deserves a talk on his own. It would be a really cool talk. And Yunyin Hu at Silicon Studios, he worked with us and really helped us bring a lot of this technology to completion. And that's my talk. Thank you. If there's any questions?
Yeah, I was wondering if you could go into a bit more detail into shader injection. And specifically, I think that it'll become a lot more easier with work wraps because of splash nodes and node renaming.
Yeah, we use work wraps a little bit. So honestly, I lied a little bit to you. So we actually realized kind of late in the system that we needed to solve transparencies as well. And so we actually do this for our transparencies. And so how we solve this issue is we take, so we actually, and this is mostly Yoon's work, so I'm a little fuzzier on the details, but we basically take the same descriptor binding. So we've upgraded the DX12 version in Unreal, so we get the better descriptor bindings. I don't remember the details of that. And then we just bind our entire descriptor set into Unreal. And then additionally, we take all of the shaders that TTRender uses, and we just we mess with the include paths a little bit so we can include all of those. And then we just have a few calls straight into there. And that actually allows us for our transparencies to get the whole same series of effects and light support. Back here?
Hey there. I'm curious to hear like what kind of features the TTRender host has and how much iteration you do in that versus in engine.
Yeah, good question. So the render host itself basically just loads an EXR and we just have a message pack buffer with like lighting parameters and renders it out. It's a pretty simple window. It does shader reloading. It doesn't actually do DLL reloading because the whole host itself is so quick to load. It was initially a lot of the work. We'd eventually do a lot more work in Unreal now. It's pretty easy to reload stuff in Unreal, especially given that most of our concerns are separate from it. It's nice for testing. We still use it. We use it as part of our CI to do testing, and then it's also pretty instrumental for doing platform ports, because then we can kind of just build and port it in isolation before we're really concerned with kind of the whole monolith of it inside of Unreal. Any other questions? Over here?
Yeah, so you've got quite an interesting setup with light rigs and specialized light masks and stuff like that. How much of that functionality did you have in your previous custom engine, and how much did you have to kind of invent fresh in this engine? And what was your approach for identifying what would be useful for artists? Because like you've got all these features, how did you know which features you need to use and would be good for the game?
Yeah, this is some good questions. So regarding how we decided what's good for the artist and what would be good for a game, honestly, there was like a bit of kind of working closely and trusting our artists, and a lot of that working on iteration, right? There would be a lot of like, let's do something, let's try to build it, let's see how it works, and let's continue from there. As far as like what was in our previous engine technology, so the light priority system, I won't say is like an exact rip of our previous system, but like it was very similar in the Telltale tool for Wolf Among Us. And so that was kind of lifted, and we had a lot of work with it. It was very, in the Telltale tool, it was very limited in that it was because for Wolf Among Us was the only game that used it, and it was a pretty long time ago. And so it was limited to like 3 or 4 lights and per character, and that was actually directly attached to the character. Whereas in this system, they can be applied to any arbitrary set of things, which is nice. You kind of mentioned Light Rigs itself, which is a system that I didn't really get into. And so how Light Rigs work, it's actually almost more of a gameplay feature, but each character has artist-controlled scriptable set that of like generally 3 key lights that are attached to them and only affect the character. And that system actually is much better in our old tool. We've tried to rebuild it in our new tool, but that's the kind of system that's like, because what that would do is it would take into account a lot of like where the camera is versus the characters versus scene lights are supposed to be, and do a lot of smarts and had a lot of like mapping to try to figure out where to put lights. And that ended up mostly being just a development time speed up, so that lighters could get much closer to a final light without a lot of investment. And that we have rebuilt that in the current system just based on schedules and what we needed to get lighters be to light on like within budgets. But I would say our old system there is probably more comprehensive and hasn't been fully ported yet. Does that basically answer your questions?
Yes.
Cool. Anyone else? Let's do here.
Yeah, the inverted lines. How do you actually do them? Do you have a texture which holds the lines for each asset, or do you have a normal map and determine where the inverted lines are and then you apply them?
Yeah, so the invert lines are the same as our outline system. I think you're asking how.
I'm asking specifically for the inverted lines.
Yeah, so the invert lines, you're asking where we get those. So they are the same system as our outlines. They are just if an outline, and so I guess I'll start with our outlines. So our outlines we have 2 main systems. So the first system is a screen space technique. At old Telltale, we had experimented with a few techniques. We did inverse hull for a little while, and then we did like a compute shader that would try to find outlines. We eventually settled on just a simple screen space technique being one of the best. We mostly rely on object ID to draw the outlines between characters as those characters in their environment, as that seems to just be kind of the most stable. And then additionally, we get from materials hand-painted lines that with some optionality we can dot product them versus the screen, so they can kind of like blur in and out. Additionally, those are encoded as SDFs, just so we can get stronger lines. That's also technology from our old engine. And then for outlines, it's basically, or for invert lines, it's basically that system, but whenever we detect that it falls into a shadow, we decide to paint it with our invert line colors rather than our standard outlines, which are generally black or sometimes blue on snow. Does that answer your question?
Yeah, I think it does.
Cool. Anyone else? Here?
Yeah, question about your lights and fall-offs of the lights. In most of the examples you showed, the fall-off is always an on or off, so there is no fall-off of the light. But I've also seen some pictures that you showed at the beginning where there is some fall-off of a light on an object. How do you handle with fall-offs in combination with the priority system?
Yeah, so I wonder if I have any good. So the lights always, are you talking specifically about fall-offs based on distance or fall-offs as they wrap around a character?
Well, maybe both, because you said it was also intensity driven, so it's one of the intensity.
Yeah, so I guess for fall-offs in distance, we almost always have pretty standard fall-offs in distance. Obviously with the gradient intensity, that can be overridden, but generally it'll be made up for with artist controls. The gradient itself will gradient to 0. And so the artist will generally tweak that so the distance normally falls off correctly. As far as wrapping around things, they generally have fall off. So it interacts with our cell shading system as well. I think maybe this big B shot. It's hard there because he has a lot of detail on him. And I think specifically, I mean, there's the ability for the artist to have a lot of control over how that should look, really. But we certainly support pretty traditional fall-offs. I mean, you can see here on his shoulder, right, you have like because there's multiple lights on him. And so like these lights and these lights all have pretty standard gradations across them. There's generally some form of fall-off. And if you don't have fall-off, that's actually I mean, we have all sorts of weird problems near. Something I didn't really get into is you always have problems when you're projecting a shadow and you still have light at a point that's perpendicular, like a surface that's where the normal is perpendicular to your shadow, right? Because like no one really solves that problem because with normal fall off, it normally goes to 0. So we've had to do a lot of work for our shadows specifically, because we do have cases where we have very little or very quick fall off. And that can cause shadow artifacting. And I don't really remember the specific details about that, but I think it was just a lot of really careful math to get right. Hope that kind of answered your question. Do you have any follow-ups?
A little bit. Yeah, of course, you still have the problem that people can turn around your character or walk with it, and you can still get those issues.
Yeah, so most of the turning around the character and stuff, things are solved by the few facts. So obviously, most of our scenes are shot-based, so you can't turn around the characters. So most of the other shots you've seen, that will be the case. And certainly when you do, it'll look a little weird. The other sorts of things is, so for instance, in this scene, you can, in fact, turn around the character. This is a free walk scene. And we play a few tricks. So there are some fall-offs which look fine. The other things is generally the light rigs themselves, they'll circle with the camera. So, and then also we have a whole set of rules that based on how the camera's moving and how the scene is, they can shift. And the artist has a lot of control over, as the camera spins, how the light rig reacts to that. Cool.
Okay, thanks.
Any other questions? How are we doing on time?
It's 2 minutes after half. So, okay, thank you, Indy.